Alright guys, so we're going to take a look at the XY equilibrium demo. So you're watching this either because we had a sub or because you missed class, so this is our makeup for that. So chemical equilibrium is a dynamic system, meaning that the rate of the forward reaction is occurring at the same rate of the reverse reaction. So when we have a reaction, we have our reactants on the left side always. We're making products on the right side, so we can go in the forward direction and make products, or we can go in the reverse direction and turn those products back into reactants, and we get a balance between the two. So even though a system is at equilibrium, that does not mean the concentrations of the reactants and products are the same necessarily. A system at equilibrium can have more reactants than products, but the forward and reverse reaction rates are equal. So the rates are equal, but the amounts of chemical aren't necessarily equal. If a system is stressed, it will shift to relieve that stress. So the purpose of this mini lab and a demonstration is to determine how a chemical system will respond to a stress and how that can be applied to every reversible reaction. The color in this system indicates the concentration of the reactants and products. If there is more reactants than products, the solution will be pink because it's going to have more of chemical X, and chemical X is pink. If there are more products than reactants, the solution will become blue because chemical Y is blue. If there are equal concentrations of X and Y, of reactants and products, then we'll have that combination of pink and blue, which will be purple. So that's when we have equal concentrations. No matter which one we have the most of, the reaction will still always get to equilibrium. So we're using X and Y to represent two really complex chemicals that we're going to be reacting in this situation. So what we're going to be doing, we're starting out with all of our solutions being purple. Okay, a nice purple color. So that we can tell that we have equal amounts of reactant and product, and then we're going to add a stressor. So over here are our stressors. We're going to add water, we're going to add hydrochloric acid, we're going to put our chemical in an ice bath and a hot water bath. And we're going to see what happens to our reaction as we do each of those things. Okay, so right now I've got 4 test tubes in my test tube rack on the side, out of sight of the camera right now. And we're going to take them individually, we're going to add those stressors, and then we're going to see what happens to each of them. Alright, so here's our first one. We've got our test tube with the purple solution in it, and we're going to add about 10 drops of water to it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Put some water in it, and I'm going to give it a shake. You can already see on the top here that it's starting to turn a pinkish color. And with these reactions, everything is called qualitative, meaning that the amount doesn't mean as much as much to us. So I can add a little bit more, and you can see that our solution is turning purple. So our stressor is we're adding water to this reaction, and it's becoming more pink. So let's look at our paper and see what that means. So on our paper, we can say for our first stressor, our initial color was purple, and then our final color was pink. Okay, so which direction did our reaction shift? Well, what that means is if we started with equal amounts of reactant and product, because it was purple, we made more of the pink chemical. So that means that the reaction shifted towards that chemical. So it shifted towards the left. Okay, you can do a little arrow if you want as well. So it's going towards the left. So what that means is that our reverse reaction, I'm going to use RXN for reaction, was faster than our forward reaction just for a little bit until it reached equilibrium. Okay, once it stops changing color, then it has reached equilibrium. We've shifted our equilibrium though. So at the beginning we had equal amounts of reactant and products. Now our equilibrium has more reactant than product, but it's back at equilibrium. Okay, now our next one is to add 10 drops of HCl. So let's take a look at that. All right, so we have a new test tube. Again, it's purple. We can see that here. And I'm going to add 10 drops of HCl, hydrochloric acid. And this is very, very strong, so I'm going to be very careful with it. And we're going to add some in there. You can probably already see what's happening with it. It likes to sink to the bottom, so it mixes really well for us. And I probably added a few more than 10 drops. But again, this is qualitative. So we can see a nice cobalt blue color coming from this. All right, we're getting that lovely blue. So as we add the HCl, we can see especially at the bottom, we're getting that nice pretty blue color. So let's fill out our table. So on our second one, we started out with the initial color of purple again. And after adding our stressor, so it was at equilibrium, we stressed it and it became blue. So that means that it shifted towards the side with blue. It made more of that chemical. So it shifted to the right. So that's our forward direction. So the forward reaction was faster until it reached equilibrium. So again, we started with equal amounts. We added more HCl, and then it made more product. So we ended up with our equilibrium having more product than reactant. Okay, so let's just talk about those two for a second. When we added water, water was a product and it shifted to the left, to the opposite side. When we added HCl, HCl is a reactant and it shifted to the right, towards the opposite side. So we can go ahead down at the bottom and fill out, let's just take a look at this first box, okay? If a blank is added to a system, the equilibrium shifts towards the blank. So let's start with if a reactant, so something on the left, is added to the system, the equilibrium shifts towards the products, okay? And if we added a product, if a product is added to a system, the equilibrium shifts towards the reactants. So in general, if we increase the concentration of something, it's going to go to the opposite side. Okay, if we add a chemical, doesn't matter which one we add, it's going to shift it towards the opposite side because it's like we have too much, so it has to use it up. And it has to get back to its equilibrium position. Okay, now we're going to take a look at an ice bath and a hot water bath. Okay, so what we have on the left here is a hot water bath. So this is nice warm water. And on the right we have an ice water bath. So we're going to put our two purple test tubes, again we're starting with that purple, down in there. I'm going to let them sit for a minute. And we're going to see what happens with the color. I'm just going to stir them around so that they get a little more exposure to the ice and the heat, and it kind of speeds up the transformation here. So let's go ahead and take a look. It says to leave it for 5 minutes, but it does react much quicker than that. We've got our nice pink solution here in the ice. And we can see over here we've got that nice blue solution in the hot water. Alright, so if you think of like your Hot Wheels cars when you were a kid, the color changing ones, or if you've ever had color changing toys, it probably has some sort of chemical in it that is shifting colors based on it having hot or cold water on it. So if you have those Barbies that change their hair color or any of that, that's what's going on with them. So we get our pink in the cold and our blue in the hot. So let's fill out our table. Okay, so our ice bath and our hot, again, we started with purple for both. So let's talk about our ice bath. That's the one that turned, oops, and I dripped water, nice and pink for us. That's gonna bleed, oh well. So our ice bath turned pink for us, and our hot bath turned blue. So let's talk about what that means. Well, we've seen before when it turned pink, that meant that the reaction was going towards the left-hand side, towards the reactants, making more of that chemical. Well, why is that? Well, heat is right there in our reaction, okay? So with that, that means for ice bath, we are taking away the heat. We're removing heat. So now the reaction's like, hey, I need my energy back. So what's it going to do? It's going to go towards the heat to make more of it. So it shifts to the left to make more heat. So that reverse reaction takes over and goes faster until it gets back to equilibrium. Okay, so it's going that way to make more heat because we took it away with the ice. Okay, and in turn it turns pink because if we're going towards the left, then we're going to make everything that's on the left. We're going to make more of that pink chemical and more of that HCl. Now we also have our hot water bath. I'm not going to drip any more water or paper. So that's the one that turned blue. Well, what's going on there? There we're adding heat. So it's like the reaction's like, hey, I have too much heat. I got to get rid of it. Well, to get rid of it, it's going to react and make products. So it gets rid of the heat by making water and this blue chemical. So it shifts towards the right. And again, that forward reaction goes faster and takes over until it reaches equilibrium again, until it gets back to its stable point. Okay, so let's fill out the bottom part, which is like our notes for this. I'm going to get a couple things out of the way. Mine's a little wet here. So we said when we increase the concentration, if we add a chemical, it's going to go towards the opposite side. Well, if we look at our temperature, that's down at the bottom. So if heat is added to the system, the equilibrium shifts towards the opposite side. Okay, towards the opposite side, right? When we added heat with the hot water bath, it didn't go towards the reactants, it went to the opposite side, the products. And if heat is removed from a system, the equilibrium shifts towards the same side. So wherever the heat is, that's where we're going to shift. So when we took heat away, it's going to shift towards that side where the heat is. In this case, it's on the left. So it doesn't mean left or right. It depends on where that heat is. So in this reaction, heat's a reactant because it's an endothermic reaction. If heat was written on the product side, it'd be exothermic, and it would shift how this reacts. Okay, let's talk about decreasing concentration. We looked at increasing the amounts of a chemical, but we can predict what would happen if we decrease it. It should be the opposite of everything that happens over here, right? So if a reactant is removed from the system, the equilibrium is going to shift towards the reactants. And if a product is removed from a system, just ignore that, the equilibrium shifts towards the products. So let's think about that. If I take away, say I took away the pink chemical, it was at equilibrium and now I took away pink, now the reaction's going to want to get it back. So we're going to use some of our products. Those are going to react with each other. So chemical Y plus water is going to make more of this to get our pink back till we get back to our equilibrium point. Till we get back to that special spot that they like. Now if I took away a product, say I took away water, it needs to get that water back. So it's going to go towards the right side. So if I maybe heated this enough to actually boil some or evaporate some of the water away, it would shift towards the product side. Or if I just left it out, right, we'd see it become darker and darker and darker blue as it tried to remake that water. So if we decrease the concentration or take something away, it's going to shift towards the same side. All right, so if we add something, it's going to go to the opposite side. If we take something away, it'll go towards the same side. That happens down here with temperature as well, right? If we add heat, it goes to the opposite side. If we take away heat, it goes to the same side. Now, pressure is for gases only. So if we see a reaction, and we're going to do a little example of it. Actually, let's write that example reaction down here. And this is a really common one that's used. Really important to put the coefficients for this. And these little G's I'm putting represent gas. what's going on here? So we've got nitrogen gas plus 3 hydrogen gas molecules forming 2 ammonia gas molecules. So when we put pressure on something, okay, pressure is when the particles hit the sides of their container. So if we imagine a little container and they're bumping into the sides of the container, that creates pressure. So if pressure is applied to a system, so if we apply more pressure to the system, then the system is, you can imagine it's under too much pressure. So the equilibrium is going to shift towards the side with less moles of gas. Okay? So it's the side with less moles of gas. So if I put pressure on something, right, it's going to want to relieve that pressure, and it's going to do that by reducing how much stuff it has in the container. It wants less stuff because it's under more pressure. So if we look at our reaction, on this side we have 4 moles of gas, and on this side we have 2 moles of gas. So in this case it would shift towards the right side if we increase pressure for this particular reaction. Okay, it won't always go to the right if we increase pressure. It just depends on where the side with less moles is. And if pressure is removed from a system, right, we relieve that pressure, we spread everything out, then the equilibrium is going to shift towards the side with more moles of gas. Okay? And it's going to do that because it has less pressure. Everything can spread out. It wants to fill up that space that it now has. So we want to maximize how much stuff we have. So we're going to go towards the side with more moles. Okay? So if pressure goes up, moles must go down. And the opposite is also true. If pressure goes down, our moles want to go up. So we want to go to the side with more moles. They're going to be opposites of each other. Okay? So this is our notes, and the practice we're doing is Le Chatelier's principle. That's what we're looking at here. So let's just take a look at the first one, since that's dealing with the same reaction we were just talking about. So Le Chatelier's principle states that when a system is at equilibrium, it's subjected to a stress, the system will shift its equilibrium in order to relieve that stress, as we just saw. The stress can be due to a change in concentration, temperature, or pressure. If a stress causes a shift of the reaction to the right, the forward reaction takes over to produce more product. If the stress causes a shift of the reaction to the left, the reverse reaction takes over to produce more reactants. Whatever the shift may be, the system will always return to equilibrium. So, let's take a look at how this example is set up here, or how the problems are set up. So it gives us a chemical reaction to refer to. We're going to decide based on the stressor which way the equilibrium is shifting. And you'll see some of the things are crossed out because they're already being talked about here. We don't have to address them twice. So we're going to determine what is the direction of the shift, and then what's going to happen to our amount of each chemical. So when we see a chemical in brackets, that means concentration or molarity. So that's saying the concentration of nitrogen, or the concentration of hydrogen, or the concentration of ammonia. So are those increasing or decreasing? So let's take a look at the first one. If we added N2, it's saying it shifts to the right. Well, we saw that. If we increase a reactant, it's going to shift towards the opposite side, the products. So it's going to go to the right. So that means that our chemical on the left, this one, we're going to have less of it as it gets used up. And our chemical on the right side, we're going to increase its amount as we make more of it. So the direction that it's shifting, and I like to kind of put a little division between my reactants and products. If it's going to the right, that's the side that it's making more of. Okay, and I divided it here because that's where my arrow would be. If I remove H2, so I remove a reactant, I am decreasing the concentration. So if I remove a reactant, it goes towards the reactants. So it's going to go to the left. So if it goes to the left, then this side is going to increase, we're going to have more nitrogen gas, and we're going to decrease our amount of NH3. Now, let's look at this one. If we remove NH3, so we're decreasing the concentration of something, so it should go to the same side as that chemical is on. So it's going to go to the right. So therefore, as it goes to the right, we're making more of that, so these are both going to decrease. If they're on the same side of the reaction, they should do the same thing. All right, our last one is adding heat. So our heat in this case is right here. It's a product. So if I add more of it, it's going to shift to the opposite side. So it's going to go left. So our stuff on the left will increase. And we're going to decrease our amount of chemical on the right. So we shift our equilibrium. So we stress out our reaction, and it shifts and gets back to equilibrium by changing its amounts of chemicals. So that's what we're doing for this and the page underneath. So be careful with those. For the very last, for the last two, you're filling in the missing information. So there shouldn't be any repeated ones in theory here. And so it's giving you something that's happening to the chemicals, and you're deciding what is the stressor and which way is it shifting, okay? Don't forget about pressure. You can look at your gases and think about pressure. If you notice that all four are changing, then that should either indicate a pressure or temperature change. If one is crossed out, then we're changing something about that one, okay? So try those out, work through that, and go from there. Thanks, guys.